All right, so I'm pleased to introduce Peter Bierhorst, a regular of Quilt Day, representing the University of New Orleans. And today he's going to tell us about his latest work on ruling out bipartite, non-signaling, non-local models for tripartite correlations.
All right, yeah, thank you, Mark. Yeah, so that's a bit of a mouthful, bipartite, non-signaling, non-local models. So my abbreviated title is just bipartite models for tripart correlations. So, this gets to sort of telling the difference between a two-party experiment and a three-party experiment. So in quantum mechanics, we have Alice and Bob experiments, and Sander was talking about that just now. Well, in so many words, two input experiments, I guess. I certainly was thinking of, this is a possible scenario where you have, a source in the middle that's distributing particles to separated people, Alice and Bob, who are measuring the things, and so they get these outputs. And so you can stylize that picture by having Alice providing an input to some system that has arrived in her laboratory and getting an output. So the input could be like a measurement setting, and the output could be whether or not a detector clicks. And Bob's doing the same thing. He has an input and he has an output. And you might have different probabilities of different setting configurations. So, if I put my hand over this little 1/2 here, this means that if, Alice inputs setting 0, she chooses between two settings, 0 and 1. And if Bob puts in setting 1, his choice between 0 and 1, then there's a 50-50 chance that they'll get the output 0 for Alice, 0 for Bob, and or the output 1 for Alice and 1 for Bob. And this particular distribution I've shown you here is that of the PR box. This is a non-local distribution in the sense that it cannot be expressed as sort of a decomposition of pre-existing classical hidden variables. You can't get this distribution if you try to remove the randomness without introducing signaling effects. And so the PR box is sort of more quantum than quantum in a sense, that it exhibits this strange phenomenon, but is quantum mechanics can approximate that to some degree, but is sort of like a noisy PR box where it's this would be the most non-local a distribution could get in a bipartite scenario with 2 inputs and 2 outputs. And quantum mechanics does sort of like a noisy version of that. And what's interesting about this is there have been experiments that have demonstrated quantum non-locality. So this property of not being able to be decomposed into pre-existing classical local hidden variables is an observed physical property in nature. And so we can say that this bipartite, non-signaling, non-locality is a physical phenomenon, non-locality shared between 2 parties, and corresponding to violation of Bell-inequalities. So now we go to a 3-party experiment, because that's maybe the next thing we might want to think about. And we want to say, okay, if I've got 3 parties, can quantum mechanics do something funny in a 3-party experiment where, Alice and Bob and Charlie, all 3 of them are spatially separated and they're measuring simultaneously. And of course, you can certainly get a scenario where the measurement outcomes cannot be described, that the distribution of measurement outcomes cannot be described by a pre-existing local hidden variable theory. You can certainly get a scenario like that if just, Alice over here and Bob over here sort of share a bipartite non-signaling, non-local system, and Charlie could just be doing something completely unrelated. He doesn't have to be doing anything. You can get something that's not expressible as a local hidden variable theory. But that wouldn't really be genuine tripartite non-locality in a sense. You would say, well, if Alice and Bob are doing just the old thing that we've already observed and Charlie's just flipping a coin, there's nothing new going on here. And so what I want to talk about today is, bipartite models for tripartite correlations. If you had a tripartite correlation that was kind of like what I just described, where Alice and Bob are doing the bipartite thing and Charlie's just flipping a coin, then we have a bipartite model for whatever the joint distribution of the three parties is. We could have sort of more subtle bipartite models for three-party correlations. And so the central question I'm sort of posing today is, what kind of distributions can be simulated by bipartite-only models, where the bipartite things are possibly non-signaling and non-local, but still there's sort of only this bipartite character to the non-locality. And then are there sort of tripartite distributions that sort of go beyond such a model? So, a model we can think about that's a bipartite model that's a little bit more complicated, as we could say, and this has been thought of in past work. We could say, well, what if we look at Alice's system? So going back to the previous slide, here's Alice's system over here, and now if we go to Alice's system, this big whole thing, we could say, what if we were to zoom in on it, and while she's measuring it, maybe what she thinks is just this one system that's sort of genuinely tripart entangled with both Charlie and Bob is actually just a collection of subsystems, and maybe there's some bipartite subsystems connected with Charlie and some other bipartite subsystems connected with Bob. And then when she measures this thing that she thinks is just one system, really what's happening is, she applies a measurement to this whole collection, and maybe the first thing that was shared with Charlie is measured and sort of has some response to that measurement that maybe induces a different kind of a measurement on the thing that was shared with Bob. And then after that measurement, maybe that sort of affects this other one, and sort of all three of these systems are maybe measured in a cascaded manner. And then there's this one overall output that, after all of that's done, the big macro system, Alice maybe sees a click or doesn't see a click. And whether or not she sees a click or not is sort of based on what was going on behind the scenes here, sort of a function of all three of these measurements. And each one of these measurements was just a bipartite system being measured that was shared either only with Bob or only with Charlie. If we could come up with a model like that for observed experimental tripartite correlation, we might say that's not really genuinely multipartite non-local. There's a bipartite non-signaling non-local model, where maybe these systems that are just shared with Bob are non-local, but they're only shared with Bob, and maybe these systems that are just shared with Charlie are non-local, but just the previously existing kind of non-locality that we've seen before. Sort of the most extreme version of which is this PR box distribution, but quantum mechanics can at least do a sort of noisy version of that. So that's our central question. What kinds of distributions can be modeled this way with this bipartite non-signaling non-local system, which is bipart only? And does quantum mechanics sort of move past such systems? Are there quantum distributions that can't be reduced to a model like this? So past work on this question has shown that there's some non-trivial tripart distributions that can be simulated this way with this network of bipartite non-signaling non-local stuff. So things that initially you would think, oh, that looks very tripartite, actually can be simulated this way. But there are others that cannot be simulated this way. And one of the more recent works showed there's sort of a testable separation here. So the first works that showed that there are distributions that cannot be simulated this way sort of showed that you can't simulate the distribution exactly. There's no quantum distribution that can exactly simulate it, but it was still an open question whether you can get epsilon close to this distribution with a bipartite model. And so this paper here from 2017 came up with a robust separation and came up with some Bell-like inequality that can be violated robustly by a tripartite quantum system, but is obeyed by all bipartite non-local non-signaling models, bipartite-only models. So my goal in the work that I'm talking about today was to sort of clarify and justify some of the arguments in Chao and Reichardt's arXiv paper that I found a little bit not fully justified, or at least I couldn't understand them. So I wanted to really, put it on firm ground, at least for my own sake. Maybe I'm being too mathematical about things, but I felt like there were some questions that needed to be answered about why certain steps followed from another. And so in doing this, I was able to sort of do a conceptual simplification of reducing the whole problem of networks of bipartite models to networks of just this one specific bipartite model called the PR box. And there was a result from 2011 that implied that, if you can say that something cannot be modeled with PR boxes, then you can also show, therefore, that it can't be modeled with any system of bipartite non-local, non-signaling systems. So this allowed, I believe, some degree of a conceptual simplification, at least for the tripartite case of this Chao and Reichardt argument. And then by putting it in sort of a rigorous mathematical framework, it allowed me to really formalize all the assumptions that were going into it and prove some things that are sort of taken for granted sometimes in previous works, such as whether or not there exists a joint distribution corresponding to a specified system of PR boxes, whether it exists and is unique, and also showing that that overall system is no signaling, and some minor modifications to make testing more experimentally feasible. So let me talk about how this worked. So I'm going to do a schematic picture of what a network of PR boxes is going to look like sort of schematically. This arrow is going to be the input to a specific PR box, which, remember, is a bipartite system shared between Alice and Bob. And so we've got the input going in as an arrow, and the output is displayed in the box. And if we have a whole network of PR boxes, and then we've got, Alice has a whole collection of things that she's looking at. And remember, this is behind the scenes. The actual experimenter maybe doesn't know about this, but there's the system being measured maybe contains these 6 subsystems, and some of them are PR boxes shared with Bob. Some of them are PR boxes shared with Charlie. And then, when Alice, just Alice, just one player looks at just their PR boxes, when they input their measurement setting, maybe they, that induces some measurement of the PR boxes. And so, here I'm showing that when Alice performs one of her measurement possibilities, we'll call that A, that corresponds to measuring the first PR box with an input of 0. And if that PR box gives an output of 1, then the whole collection of subsystems will induce a measurement of the second PR box shared with Bob, and then it'll proceed to the other PR box shared with Charlie, so on, so forth. But if that first PR box shared with Bob shows a 0, maybe then the way later measurements progress is a little different. And the second PR box shared with Charlie is what's measured, and that might show 1. And so based on all these things, Alice could be taking some funny path through her PR boxes based on, results of earlier ones changing how it goes. But you can model all of that as a decision tree. So Alice has some big setting that she puts in. Think of this as what the experimenter actually does. That's going to be the setting X. And based on whatever that overall setting is, that might determine which is the first PR box that's measured in this collection of subsystems. And then, we have a decision tree that's showing all the different ways that one goes through the PR boxes based on early measurements. And so this completely specifies, what a player's strategy could look like given a bunch of PR boxes. Okay, so now assume that each player has a decision tree like this, right? So there's Alice, Bob, and Charlie. Each one has a decision tree like this. This completely specifies how their subsystems are going to be measured in a sort of cascaded manner, and it depends on their local setting, how that cascade starts, and there's all these different branching things. So if each person has a decision tree like this, we can ask, what does the joint distribution look like? And so, and then there's some questions, is there a joint distribution, right? And some funny things about this might not seem immediately clear as we say, well, what if, Alice moves through all of her PR boxes first, and then later Bob moves through all of his? Do we get the same thing, the same overall joint probability distribution if Bob moves through all of his PR boxes first, and then Alice moves through hers? And we have an indefinite causal order because in an experiment where these things are measured sort of simultaneously, or close to simultaneously, and they're space-like separated, we can't really say this player actually went first. We have a relativity problem there. And so in quantum mechanics, the structure of quantum mechanics kind of tells us that everything will be okay, kind of the way it's set up, but it's less clear when we're talking about these PR boxes, which are non-physical entities. So we want to make sure that we're not assuming anything along those lines. So the way to build the joint distribution is first to formalize assumptions for joint distribution, we just assume for now that there is some ordering of players in which they measure their PR boxes, and that as they encounter the PR boxes, the distribution of each subsequent PR box is uniform, conditioned on PR boxes already measured. So as Charlie is the first player, he works through all of his PR boxes, he sees 1/2. And then as Alice, maybe the second player, works through, then the PR boxes she measures that are shared with Bob are all going to be uniformly distributed as she encounters them. But then the ones she shares with Charlie are actually going to be fixed by whatever he already saw. That's kind of how PR boxes work, is that if you know both inputs and you know one player's output, then you know the other player's output with certainty. And then the last player, as they work through their PR boxes, all of their PR box outputs are going to be fixed because the other players have already gone and observed the PR boxes. And so that fixes the outputs that the last player sees. And so then the question is, I've chosen an arbitrary order here, and this gives me a way to build a joint distribution for all of the PR boxes. The question is, if I had chosen a different player ordering, do I get the same joint distribution? So I'll return to that question in a minute, but just talking about this joint distribution, what are some things that we see first? Well, let's look at the first player. And they says that, a single player's distribution is uniform. So if this is sort of the outputs that, here's just a random assignment of 0s and 1s to all the things that Charlie might see as they work their way through the PR boxes. And if Charlie has a well-defined decision tree, that's going to correspond to exactly one path through his PR boxes, right? So if we just uniformly assign 0s and 1s to everything Charlie sees, you can think about it, then that's going to, take him through the decision tree some way or other, right? And then this assumption here is going to ensure that when we multiply all those conditional probabilities in sequence, that we get a uniform distribution on being on this particular branch. So a single player's distribution is uniform. A pair of players has 3 degrees of freedom. So this is sort of interesting. We can imagine assigning, for each shaded square, imagine assigning a 0 and a 1. And then you say, is there some path through the trees that's consistent with this assignment of 0s and 1s? And well, first Charlie goes, and that takes him on some branch. And then as Alice goes, she encounters these boxes over here that are shared with Bob, who hasn't gone yet. And so whatever we shaded in for that takes her through some, path through her boxes. And that as she encounters those, they're uniform. And then when she moves to boxes shared with Charlie, those are going to be fixed by whatever Charlie already saw. But for anything in this black shade, for any values of 0 and 1 in this black shaded thing, there is a branch of Alice's tree that will correspond to these black shadings in Charlie's already set thing. So a pair of players has 3 degrees of freedom, and this gives us some ways to start thinking about the joint distribution and properties that it obeys. And finally, the last player is determined. We have this ordering where Charlie goes first, everything's uniform for him. Alice goes second. Things that she shares with Bob are uniform. Things that she shares with Charlie are determined. But then for Bob, everything's already been measured on the other side. So he's completely determined. And the way these things all work help us prove things later. And then, one can prove, and I showed this, that the joint distribution is player order independent. So the joint distribution of all sort of possible combinations of 0s and 1s for all players. So not all things are uniform. Not all 0 and 1 combinations are possible. Only some of them are. And the joint distribution of all the possible ones and the probabilities you'll get the same joint distribution if you work through the players in any different order. I have a figure in the paper that kind of shows it by switching between these two ideas. This is Charlie going first over here on the left. This is Alice going here on the right. And you can kind of see that you'll end up getting the same thing. I won't go into that. And this is another figure from the paper where I argue about why they're independent. And so once you've proved that the joint distribution is player order independent, you get some nice things that you can now. Joint distribution is no signaling, right? So I've seen this claimed in a lot of papers, but everyone just seems to take it for granted that if you wire together all these PR boxes, then of course the joint distribution would be no signaling because everything individually is no signaling. That was never immediately obviously clear to me. To some people, maybe it was, I don't know. But you can actually prove it by, approaching the problem in this way. And the way you prove it is you just say, well, assume, if I want to say that Charlie is independent of Alice and Bob, then you can say, assume an order where he goes first, and then everything he sees is uniform, completely independent of whatever they do. If I want to show that Bob is independent of the other players, assume he goes first. And now having proved that there's a unique joint distribution, and it's the same for whichever player goes first, you can sort of assume that any player goes first, and you've shown that their distribution of PR box outputs is uniform, regardless of the strategies of the other player. And so the strategies can't change that player's distribution. You get no signaling. So a lot of these properties, these no signaling properties are useful. And then using properties such as a pair of players has 3 degrees of freedom, sort of how these things functionally depend on each other, you can prove or rederive the Chao and Reichardt inequality. So I went through this proof. The proof that they had, I kind of went through a lot of these steps that were outlined in this work and translated it into my framework and kind of went through the proof. So I'm now satisfied with this proof. And so we have an inequality. And the inequality says that if you take this Bell function, and there's, here's Alice, Bob, and Charlie, and each one of them has 2 different measurement settings, which is either unprimed or primed. And so there's 8 possible measurement configurations for the whole thing. And then each person can have either a plus or a 0 outcome for the whole thing. After the PR boxes have been measured in the subsystems, there's some overall output that's a function of the PR box outputs, and that'll be a plus or a 0. You can show that for any bipartite non-signaling network of these PR boxes that this particular Bell function, the expected value of this Bell function, which assigns this number to this particular setting and outcome, that if there's equiprobable settings, that the expected value of this Bell function has to be greater than 1/8 for bipartite non-signaling non-local networks, and that there's also a quantum state that violates that inequality. This is strictly less than 1/8, which is 0.125. And the fact that this violation is, a strictly positive number means that if you can't do this quantum state exactly, but can get in within some fidelity of it, then you'll still be able to violate this inequality, sufficiently close experiment. So, and this is the state that induces the quantum violation. So it's a GHZ state with Alice and Bob doing these Pauli measurements, or Alice and Charlie doing these measurements, Pauli Z and Pauli X, Bob doing these. It's reminiscent of the CHSH measurements. And these are the probabilities you get where these script C and script S are given by these formulas. And this is the thing that gives you this violation from the previous slide. It's less than that 1/8 value. So conclusions, bipartite non-signaling non-local networks can be ruled out by tripartite QM experiments. So everything I spent the whole time describing with these PR box networks, anything like that has to satisfy that 1/8 bound, but quantum mechanics can violate that robustly. I feel like this is a good candidate definition for genuine tripart non-locality, where we'd say, how do we know we've seen something that's genuinely tripart non-local? When I think that something that can not be expressed by such a bipartite network has at least some flavor of genuine tripartite non-locality. And then for future, and here's another interesting work on that by Rob Speckens gave a talk about this paper at the recent March meeting with sort of a related thing where the players don't share PR boxes, but they share sort of entangled states. It's a little bit of a different take on that. And so then, future work, can we get a better characterization, a complete characterization of the space of bipart simulable correlations? And, can we run some experimental tests on this? Is this particular inequality, is this state just way too hard to try to actually create in a relevant experimental scenario, or are we, can we do it? It would be nice to do it. It's an experimental test. Okay, so that's it. Thank you. I think I did this in 20 something minutes. Yeah.
All right. Thanks, Peter, for your talk. It's very interesting. Are there questions for Peter?
Hey, Peter. I had a question. I've seen this result that there are tripartite distributions that are non-local, but whenever you marginalize over any of the parties, the resulting bipartite distribution becomes local. So what's the relationship between that and this? Is it possible to get such distributions with the sort of networks that you're describing?
I wish I could press pause on the universe for about 10 minutes and then answer your question, because I'm wondering if this particular thing satisfies that particular condition. I don't think it does. I think this particular distribution, I believe, would exhibit bipartite non-locality between Alice and Bob, even if you marginalized over C, I think. So,
sorry, let me interrupt. This arises from a GHZ state, right? And if we trace over one qubit of a GHZ, we get a separable state. So does that present a problem with this, or am I thinking incorrectly? You see what I'm saying?
I do. Again, I don't have the pause button. I wish I could. So if we just throw away one player's measurements for a GHZ state, then no matter what you do, you get a separable state for the other two players. That's true.
Yeah, I mean, I understand. If you marginalize over distribution, the full distribution results from a measurement channel, which is a trace preserving map. And then the effect would be to propagate through and trace over 1 qubit of the GHZ state. This is my guess.
So if what Mark is saying is correct, then Victor, then this would be a scenario where tracing over, that any two parties have a, what you call local,
Yeah.
But
We do know for like the W state, I believe, when you trace over 1, you're left with something entangled, and so maybe that could be used somehow.
but I thought your point was that this GHZ state can't sort of be simulated by this PR box network model.
Mm-hmm. Yeah, I mean, it would certainly be interesting to see if, like, these non-simulable distributions always have this property of sort of this locality of the two. I just haven't really thought about that. If you could send me a link to sort of the paper that you're thinking of with this, these 3-party things that are always local between 2 parties, I would be interested in thinking about that.
Okay, yeah, thanks. I'll send you a link.
Mm-hmm.
I have a comment on something that may be related. There are quantum mechanical 3-body bound states, although none of the 2 bodies are bound. These are called Efimov states.
Mm-hmm.
And that happens in a quantum system.
Yeah, so I wouldn't be surprised if you could sort of come up with some sort of a PR box model for something like that, because the PR box in the bipartite scenario is more non-local. But the interesting thing about using these PR boxes is they're not necessarily always more non-local than quantum states, in the sense when you go to these multi-party type things, because you can't really do teleportation with PR boxes. You really need to be able to do like an entangled measurement. And that's sort of verboten for PR boxes. You can't really come up with a coherent system where you can perform entangled measurements on these PR boxes. So it's not, these things that are these quantum states that are like Ravi described may not admit, may be a good candidate for not admitting one of these PR box models.
Right. If there are no further questions for Peter, thank you again for the nice talk. And we'll transition to Ilya Vector. If you could just